We have traced the long and fascinating history of drone technology, from this earlier concept origin to the pivotal breakthrough that launches its golden age. Now, let's begin on our focus to the present day and examine the incredible state of drone industry as it stands right now. To put it in simple, the last decade has been nothing short of a revolution. We move from the niche market to the harvest and the defense contract to a full-blown global industry that reshapes how we work, create, gather information. The growth has been explosive and it's powered to converge the powerful technology drivers. Let's start with the dramatic indicator of this growth, the market value. As we see the chart, in 1916, the global drone market was valued around 2 billion. That is a substantial number. But what happens in the next is truly remarkable. In 2020, just 4 years later, the numbers have skyrocketed to 20 billion. That is 900% increase. It is difficult to overstate what kind of growth measure. This is a gradual upstick. It's a paradigm shift. This surge represents the technology reaching a critical mass, a tipping point where its value becomes undeniably a vast range of industry. So, how did this happen? We see a few key adaptation trends that paint a clear picture. The first is the global availability. The drones are no longer rare or exotic. They are widely available to all over the world with the user base that spans from young children learning to fly their first toy to young adult and seasoned professional operating highly sophisticated systems. This widespread accessibility is crucial. On the other hand, continuing to serious serious military application. As the slide notes, approximately 10 countries have actively using military-grade drones, pushing their boundaries of what is possible defense and intelligence. But on the other, the most exciting trend is the rapid technology evolution in the civilian sector, particularly with the development of AI-powered drones. This is a cutting technology where drones are becoming not just a flying camera, but a thinking, learning, and decision making platform. This explosive growth wasn't an accident. It was propelled by a perfect storm of six key market drivers, which is imaging technology. The quality of the camera has increased exponentially while their size and cost have plumbed. We have now put professional grade camera and advanced sensor on a small affordable platform, which has unlocked countless applications in filmmaking, inspection, and mapping. Second is the connectivity. Better radio link and now integrated with 4G and 5G technology, which means drone higher, can fly higher the, and stream higher quality data, and the video back is real time from almost anywhere. The third we have discussed is the battery innovation. The push for better batteries is relentless. Every improvement is energy density, meaning that it has longer flight time, which translate directly to 1 hour more work done and more area covered and more complex mission in a single charge. The fourth is the regulation. As the government around the world have established clear rules for communication drone operation, we have created a stable, uh, predictable environment. This regulatory clarity gives the business the confidence to invest heavily in drone technology. The fifth is the integration of artificial intelligence. This is a mass driver. AI is enabled advanced obstacle avoidance, allowing drone to navigate to complex environmental safety. It provides follow me more to action sports and cinematography. And the most important, it starts to analyze the vast amount of data that the drone collects autonomously, identifying the crop diseases for the farmers or crack in the bridges for engineers. Finally, the sixth driver is ties all them together is the cost reduction. The mass production of components for the smartphone industry combines their furious competition in the drone market itself has incredibly pow- has made incredibly powerful technology affordable for the individual and the small businesses, not just for the large corporation. It is powerful combination of better performance at low cost that is truly democratized the sky and fueled the 900% growth that defines the current vibrant state of the drone industry. Right? We have covered the history, a key milestone and the current state of drone industry. Now, let's get down to the fundamental of the flight itself. How much a drone can stay in air and move with such precision? The answer lies in the physics, specifically in the four fundamental forces that constantly acting on drone from the moment it leaves the ground. As the slide shows, these are the forces that are lift, gravity, thrust, and drag. Think of them as being constantly dynamic in tug of war with each other. Every movement of the drone makes it as a result of carefully managing the balancing of these four forces. For any pilot or a designer, understanding the aerodynamic stance is a absolute critical for safety and effective operation. Let's start with the most intuitive pair of forces, the vertical battle between the gravity and the lift. Gravity is one of the force which we are familiar with. It is a constant downward pull that the earth exerts on every object, including the drone. It is relentless and it is a primary obstacle to flight. To get off the ground and stay in air, a drone must generate an opposition force. The force is lift. Lift is an upward force that directly counteracts the gravity. On traditional airplane, this is mostly generated by the shape of the wing, but on a multirotor, the lift is generated almost entirely by the propellers. Each propeller is essentially a small spinning wing or an airfoil. It spins, it is designated to push large volume of air downwards. Thanks to Newton's third law of motion, for every action, there is an equal and opposite reaction. Pushing the air downwards create an equal upward force, the force that lifts the drone. When the drone is hovering perfectly still, the force of lift generated by the propellers is exactly equal to the force of gravity pulling it down. To climb, pilot increases the speed of the propeller, generating more lift than the gravity. To descend, that to the opposite. Now, let's look into the horizontal battle, the push and pull between the thrust and drag. Once the drone is airborne, we need to weigh it move forward, backward, or side to side. This is where thrust comes into play. Thrust is a force that propels the drone in specific direction. For multirotor, creating a thrust is an indigenous trick. To fly forward, the drone doesn't have a separate engine pushing it from its behind. Instead, the pilot steadily tilts the entire aircraft forward. For the lift being generated by the propellers is no longer pointing straight upward. It's angled slightly forward. This angled forces can be broken down into two parts. The vertical component and that continues to the counteracting the gravity, and a new horizontal component that pushes the drone forward. A horizontal push is thrust. The steeper the tilt, the more thrust is generated, and the faster the drone accelerates. Of course, as we do, the drone starts moving, immediately counteracting the position force of drag. Drag is essentially an air resistance. It is a force of atmospheric push back against the drone as it tries to move through it. The drag is influenced by drone shape, its cross-sectional area, and most importantly, its speed. The faster you fly, the greater the force of drag becomes. In order to fly at a constant speed, the force thrust pushing forward must be perfectly balanced with the force of drag resisting it. To speed up, the drone must generate more thrust than drag. Every aspect of flight is a continuous adjustment of these four forces. The drone autopilot is making thousands of calculations every minute, every second, adjusting the speed of each individual motor to maintain its dedicated equilibrium. Whether it's hovering in steady breeze or flying in a complex pre-programmed mission, this fundamental understanding is what separates a good pilot from a greater one. Now that we have a firmer grip on the four fundamental forces that makes the flight possible, let's explore how drones actually move and maneuver in three-dimensional space. Do you think we need to understand the three principal axes of flight? Imagine three invisible lines of axis running through the center of the drone, all intersecting at the center of gravity. All of the drone moving parts are simply rotated around one or more of these axes. As the slide states, understanding these is absolutely critical for effective control and maneuveration. Mastering how the command rotates about the axis is the very essence of learning to fly a drone. The first axis is the roll. It is the rotation around the longitudinal axis, the line that runs straight from the nose of the drone to its tail. When the drone rolls, it tilts and backs from side to side. Imagine one of the drones dipping down while the side uh, rises up, just like a seesaw. On the traditional plane, this motion is controlled by the flaps of the wings called as aileron. But on multirotor drone, it is achieved through the principle called as differential thrust. To make the drone roll to right, the flight controller increases the speed of the motor on the left side and decreases the speed of the motor on the right side. This creates an imbalance of the force, causing the left side to rise and the right side to dip. The primary purpose of the roll for a multirotor is to move sideward, a maneuver often called as starfing. By rolling the drone angle, it mainly lifts the force of the side, creating a sideward thrust that pushes it left or to the right. Next, we have pitch. This rotation around the lateral axis, the line that runs from one side of the drone to the other side, like a wing tip to tip, pitching the movement that makes the drone nose point up or down. This is the primary control for moving forward and backward. When the pilot wants to fly forward, the commands the drone to pitch its nose down. On the airplane, this is done by elevators on the tail, but on the drone, it's done by the differential thrust. To pitch the nose down, the motors of the rear drone spins faster, lifting the tail up and causing the nose to dip. This is well learned when discussing the four forces creating forward thrust. To slow down or fly back, the pilot commands the drone to pitch its nose up by speeding up the front motor. The degree of pitch directly controls the drone's acceleration and the speed in a forward or backward direction. Finally, we have yaw. This is a rotation above the vertical axis, the line that runs straightly down the top and bottom of the drone center. Yaw is a flat turning motion. Imagine spinning around an office chair or shaking your head. No, the aircraft turns left to right without a tilt or a wag. This is how the drone changes its heading to the direction its nose is pointing. While you can see these rolling and yaw pitch essentially is a precise orientation of the drone. For example, to for example, to aim this camera to a perfect shot without changing its position in air on an airplane, it's controlled by the rudder on the tail fin. On the drone, the physically are bit clever. The propellers of the drone are set up in pairs and makes clockwise and anti-clockwise in to cancel out Each rotational forces are tapped during the stable hover. To yaw to the right, the flight controls the speed of the motor spinning in one direction and slows down the motor spinning in opposite direction. This creates an imbalance in the torque rotation in the torque force, causing the entire drone to twist and yaw around the vertical axis. In summary, each maneuver of the drone performs is a combination of simple rotation, the roll for side to side movement, pitch for forward and backward movement, and yaw to change direction. The true beauty of multi-rotor design is that all of this achieved through a single elegant principle of precise variation of speed of each motor. Having explored the universal forces and the axis that governs the flight, we now look at the most, we now have the principle are applied to different types of aircraft. The word drone is a very broader term and it encompasses a wide category of design. The physical form of the drone is not arbitrary. The design is purposefully engineered to excel at specific type of mission, just as you would use a race car to haul a cargo, you would use different types of drone for the same job. The industry classifies the drone into three categories based on how they fly. The fixed wing drone, the multi-wing drone, and the less common but the important lighter than air system. Understanding the distinct advantage of the each is the key match to the right tool to the right task. Let's start with the design that the most people pictures when they hear the word drone. The multi-rotor configuration. There are quadcopter, hexacopter, and octocopter. As their name suggests, the design is defined by the number of propellers they have in them. Their entire ability comes from the flight of generating the lift by the rapid rotation of the blade. Their superpower is without a doubt is maneuverable by its rotating blade. By precise and independent controlling of each motor, a multi-rotor drone can achieve incredible feats of agility. It can take off and land vertically in a smaller space, hover still perfect, and fly forward and backward, sideward, and rotate 360 on a spot. This level of precision control makes them an ideal choice for many applications. For aerial photography and cinematography, the ability of hover and frame the perfect shot is valuable. This agility makes them the star of the high-speed drone racing world. And for the task like small package delivery in a complex urban environment, their vertical takeoff and landing capability are essential. The trade-off of this amazing maneuverability is typically a short flight time and a lower energy efficiency compared to the design. Yes, we have fixed wing drone. These drone looks much more like a traditional aircraft. These fly in a similar way. The critical difference here is the source of the lift. Unlike the multi-rotor, the fixed rotor drone is primarily generated by its fixed wing as the air flows over them. The main propeller job is to provide vertical lift, but to provide a forward thrust, pushing the drone through the air fast enough for the wings to generate the lift efficiently. The design principle makes them a marathon runner of the drone world because the wings are doing the work by keeping the drone aloft. These systems are far more energy efficient than multi-rotor. This translates directly to main advantage, higher speed and much higher flight endurance. The flight drones can cover a vast distance and stay in air for a longer time period. The far longer the capable of multi-rotor. This makes them perfect suited for large-scale mission like agriculture mapping of huge farms, inspecting long pipelines or power lines, and constructing a broader area surveillance and surveying.
Their main limitation, however, is that they can't hover. They are always in a forward motion and typically requires a runway or a catapult to launch and a large opening area to land. Finally, we have the third category, lighter than air system. There are essentially unmanned glimpses of drones. This method of flight is completely different from the other two. They don't rely on aerodynamics or for lift. They rely on the principle of buoyancy. These drones are filled with lifting gas like helium, which is less denser around the surrounding air. This density creates a buoyant force that causes the aircraft to float effortlessly, overcoming gravity, which lift takes off carefully by the propulsion system of the drone. Like small propellers or rudders are only needed to steer and hold a position against the wind. The supreme advantage of the design is extreme endurance, since they don't expand energy into to stay aloft. Lighter than air system remains airborne for incredibly longer period, days, weeks, or even longer. This makes them ideal performer for long-term persistent surveillance over a specific area, continuous environmental monitoring, or acting as a, a floating communication relay station. Each of these three designs represents a different solution to a different flight, optimized for unique set of missions. We have just discussed the three fundamental classification of drone: the multi-rotor, fixed wing, and lighter than air. This category gives a good start, but the true genius of the modern drone technology engineering lies in how we bend and bend these designed to create high specialized tool. The reality is many real-world missions have requirements that don't live nearly into one box. You might need a longer range endurance of a fixed wing, but operate in an area with no runway, a place where only multi-rotor could take off. This slide dwells into the fascinating world of specialized drones, which are optimized with unique configuration to conquer the special operational challenge. The first and the foremost fundamental specialization to understand is between how the drone takes off the land, and this leads to two primary categories: VTOL and HTOL. HTOL stands for horizontal takeoff and landing. This is the traditional airplane model. It needs a runway or a launch catapult to get up to speed and generate lift over its wing. And it needs a clear flat area to glide for landing. This is simple and efficient for fixed wing drone and operates in an open space. However, the future of many application lies in VTOL or vertical takeoff and landing. A VTOL aircraft can take off, hover, and land vertically just like a helicopter. Its capability in a game changer because it eliminates the need of runways, allowing sophisticated drone to operate for smaller, clearing a forest, a ship deck, or a roof in a denser city. The challenges and the focus of immense innovation has been combination the endurance of the fixed wing with the convention of Ito. This quest for both for the best of the both world, we lead to some of the incredible hybrid design that uses indigenously tilt mechanism. These aircrafts have essentially transformed in midair. The most famous example is the tilting rotor. In this design, the propeller and the rotor are mounted on a pod that can pivot. For takeoff and landing, the rotor points straight upward and providing a vertical lift during the multirotor. Once airborne, these tilt forward transition into the propeller and provides an horizontal thrust, and the aircraft flies like a conventional airplane on its wing. This gives a fantastic range and a speed combination with helicopter-like feasibility. A similar but distinct approach is the tilt wing. Here, it is not just the rotor that moves, but the entire wing surface rotates with them. The wing point vertical from takeoff and pivots horizontally for forward flight. The design can offer advantage in controlling airflow during the trickier transition phase between the tilt, vertical and the horizontal flight. The more traditional, the more radical solution is the tilt body, where the entire fuselage of the drone rotates for vertical flight, and an approach that showcases the incredible diverse of the engineering solution being explored. Beyond these hybrid VTOL designs, there are other specialized configurations. Classic helicopter UAVs is a prime example. While multi-rotor uses multi-simple propellers, helicopter UAV have a single large rotor which is called the collective pitch control. This means the angle of each individual blade on this main rotor can adjust in real time. This makes them significantly more efficient and capable of carrying much heavier payload than the multi-rotor of similar size. This is why you see them in in most of the mission that requires heavy sensor package for a longer time loitering, such as in depth wildlife monitoring. As the slide summarizes, this specialized design directly addresses the needs of specific application. The tilts being drawn with the efficient and VTOL capability is perfect for precision agriculture, where it can take from a small farm clearing them and then covering a large 100 acres of area for crop monitoring and health checkup. These are small, agile multi-rotor UAV is ideal tool for urban inspection, able to navigate the complex urban canyon between the building and gets up close to the bridge or the building uh, facade. And the quiet efficiency of the helicopter UAV make it perfect makes it perfect for wildlife monitoring, allowing the researcher to observe animals in their natural habitats with minimal disturbance. The key takeaway is this that the shape of the drone follows its function. This follows on this focus on the specialized design in what unlocking the full potential of the drone technology, creating enhanced capability to solve problems in even most challenging environments. We just looked at how drones can be specialized into unique hybrid form to tackle specific challenges. Now let's take a deeper dive into the most important fundamental classification, the fixed wing drone. If the multirotor is the agile sprinter of the world, capable of intuitive maneuver in tighter space, then fixed-wing drone is an endurance athlete, the marathon runner built for speed and distance. While there may be a common in consumer space, in the world of large-scale commercial, industrial, and scientific work, fixed-wing platforms are indispensable workhorse. Let's explore the core principle that makes them so effective and significant advantage that leads from their design. The design philosophy of fixed-wing drone is right in its name. It's it's rigid wings and it looks like a traditional airplane because it operates on exactly the same principle of aerodynamics that governs the flight over a century. This is the most critical instinct to understand. Unlike the multirotor, where the propeller provides direct vertical lift, the primary job of the propeller on the fixed wing drone is to generate thrust, pushing or pulling the aircraft forward through the air. The job of generating lift is left entirely to the wings. So, how the wing accomplish this? This all comes down to the air. specific shape, what known as the airfoil, and the principles of physics. As the drone moves forward, the air over and under the wing. The wing is curved on the top and flat at the bottom. This shape focuses the air passes over the top to travel longer distance, making it more faster than the air passing under. The faster motion in the air creates a low pressure. This results in pressure difference, create the wing pushing up and lower pressure during below the above the wing pulling up. This upward force is lift. But the key, as the slide notes, this is the process of requiring forward velocity. A fixed wing drone cannot create lift while standing still. It must be constantly moving forward for its wing to work, which is the fundamental reason it cannot hover like multirotor. This design choice relies on the wing for lift, leads to the cascade of power advantage. The most significant of these is the longer flight time. This come to energy efficiency. Once the fixed drone is at its crucial altitude, its wings are doing the heavy work for the counteracting gravity almost for free. Simple by gliding on the air. The motor only needs to supply enough thrust to overcome the air resistance or the drag. This vastly more efficient than multirotor, whose motor must constantly do the heavy lifting work, and it requires huge amount of energy to actively beat the air into submission and fight gravity every second. This efficient advantage means flight time for fixed are measured in hours, not not just measured in hours. It's to hours in time. This incredible flight duration directs enable directly enables their next key advantage, long range capability. If your drone can stay in air for hours or at a time, it can cover an immense amount of ground. This makes the fixed wing platform only logical for mission that spans a wide area, such as creating a detailed map of agriculture inspection pipeline that runs for hundreds of kilometers, or conducting an environmental survey over large national park that also is capable of high speed. This sleek aerodynamics are designed to minimize drag and slice through the air efficiently, allowing them to travel between points much faster than multirotor. Finally, they often have lower wing for a given capability because their design is so efficient. They don't need multiple heavy motors and massive battery that multi-rotor would require to achieve similar flight time, often resulting in lighter and more portable system for long-range mission. In essence, every fixed-wing drone strategically trades the ability of hover over unparalleled gain in endurance, range, and speed. Building on our introduction to the fixed wing drone, let's focus on the specific tangible advantage that makes them superior choice for wide range of critical mission. We have established that their design is a fundamental difference from a multi-rotor, and it forms these design difficult that significant strength emerges. We explore why these flight efficiency is high and then dwell into two unique capabilities that are largely exclusive to fixed wing platform. The ability to glide and the option to use fuel engine. These advantages are precise. Why? For certain application, there are simply no substitute for fixed wing drone. As we discussed, it's As we discuss, it's all begin with the higher flight efficiency. This is the foundational advantage from which all others stem. To quick recap, because the wings are generates the lift through a aerodynamic shape, the propulsion system only has to provide the forward thrust to overcome drag. This is a far less energy intensive task than what a multirotor faces, where the motor are in constant power hunger battle between the gravity just to stay in air. This inherent efficiency is the key that unlocks the other major benefits of fixed wing platform. The most direct result of the efficiency are, of course, the extended range and flight time. Less energy consumed per minute makes more minutes and often hours in the air, allowing these drones to cover a vast distance that would impose for their multi-rotor counterparts. Now, for the unique advantage that dramatically enhances both efficiency and safety, gliding capability. This is something a multi-rotor cannot afford. For a multi-rotor, loses power to its propeller, it falls down to the ground. The fixed wing drone, however, can glide by pitching its nose down slightly. It can convert its altitude into its potential energy into forward motion or a kinetic energy, allowing maintaining the airflow over the wing and continues to flight under the control, just without power. This is a huge benefit for efficiency. A pilot can intentionally cut power to the motor and glide for a longer stretch of mission, conserving the precious battery life or fuel, and further extending the drone's range. For safety, it provides a critical lifeline. In the event of an engine or power failure, the pilot doesn't lose control. They can guide the aircraft to a safe landing zone, protecting the valuable equipment on board and anything or anyone on the ground below. This ability to glide carefully without the power is the fundamental game changer. The other massive advantage is the fuel engine compatibility. While many fixed wing drones uses electric motors and battery, their design is perfectly suited for housing small, efficient internal combustion engine. This is a domain where multi-rotor can't compete, as they rely on instantaneous precision speed changing of electric motor to maintain stability. The benefit of using fuel engine is all about energy density. The small amount of liquid fuel contains more energy than even advanced aluminum lithium polymer battery of the same weight cannot provide. This allows a momentary leap in the endurance, while the battery-powered fixed wing might fly in few hours, and the fuel-powered version can allow for 20, 50, or in case of an advanced military system, well over 24 hours. This unlocks true long-range mission, like monitoring the entire coastline, conducting a multi-day surveillance, or even crossing larger bodies of water. As in the comparison table of the slide clearly shows, the choice between the platform comes down to the mission. While the multirotor is limited in range and cannot glide, it offers unparalleled hovering capability. But when the mission requires a higher possible efficiency, the safety net is of gliding, and the extreme endurance offered by fuel compatibility. The advantage of fixed-wing drone makes it undisputed champion of any long-distance application.